Welcome to this explainer. Go ahead and snap your fingers for me, right now. Just snap them. Pretty simple, right? It feels literally instantaneous. But beneath that one totally effortless little snap lies what is genuinely one of the most astonishingly complex biological architectures in the known universe. Today, we're going to unpack exactly how an abstract thought in your head becomes a physical reality in the world. We're exploring the human body's command chain of movement, this incredibly sophisticated system that takes your high-level goals and translates them into the precise mechanical force of your muscles. So here is our roadmap for this anatomical journey. We'll hit 1, the hierarchy of movement, then 2, planning in the motor cortex, 3, descending spinal pathways, 4, the spinal cord execution, and finally 5, basal ganglia and cerebellum. Okay, let's dive into this. Section 1, the hierarchy of movement. Let's start right at the absolute highest level of our command chain metaphor. When you decide to move, your brain actually follows a very strict 3-tiered chain of command. Think of it like a corporation. First up, you have the strategy level. This is the CEO. It involves the association areas of your neocortex and the basal ganglia, and their job is just figuring out what the abstract goal is. Next, we drop down to the tactics level. This is where the motor cortex and cerebellum step in to translate that what into the how, figuring out the exact sequence of muscle contractions you're going to need. And finally, you reach the execution level, down in the brainstem and spinal cord, which actually triggers the physical movement itself. Section 2, planning in the motor cortex. All right, so the CEO has set the strategy. Now we're moving to middle management in the frontal lobe. Right here on the precentral gyrus, we've got the primary motor cortex, or M1 for short. M1 is super important because it has the absolute lowest threshold for eliciting movement if you were to electrically stimulate it. It's organized somatopically, which is just a fancy way of saying it forms a literal motor strip, where specific regions of your body are systematically mapped out. Now, just rostral, or just in front of M1, is Area 6, which handles your skilled voluntary movements. And Area 6 splits into 2 distinct branches. You've got the premotor area, or PMA, managing proximal motor units like your shoulders and trunk. And then you have the supplementary motor area, the SMA, which is absolutely critical for planning complex sequences for your distal units. Think of tasks that require you to coordinate both of your hands at once. All of this builds into an actual chronological firing sequence. It's a literal ready, set, go process. Your mental readiness, the ready phase, relies on the parietal and frontal lobes coming online. Then the set phase kicks into gear. This is where strategy and planning happen, in the SMA and PMA. And what's totally wild here is that neurons in these areas start firing long before your body actually moves even a single millimeter. They're revving the engine. Finally, the go command is pushed through via subcortical inputs and gets executed by M1. Now, I want to slow down for a second here, because to really understand this stuff in depth, we have to talk about how M1 actually communicates. It's so easy to imagine the motor cortex like a piano keyboard, right? Like you press one specific neuron key and one specific muscle twitches. But actually, scratch that, that's not how it works at all. M1 doesn't use a simple one-to-one mapping. Instead, it relies on a fascinating process called population coding. The neurons in M1 are broadly tuned to movement direction. So to calculate the exact direction and precise force of your movement, your brain basically averages the votes of a massive population of active neurons. It's a literal neurological democracy. One neuron might vote really strongly for moving your arm left, while another neuron throws in a weak vote for moving it up. Your final movement is the calculated mathematical average of thousands of these broadly tuned neurons shouting all at once. Section 3, the descending spinal pathways. Okay, so the motor cortex has calculated its tactical orders, and now those orders have to travel down the information highways of your body. Basically, this information travels down 2 completely different major highway systems. On one side, we have the lateral pathways. These are under your direct cortical control, handling the voluntary movement of your distal musculature. You know, like those snapping fingers we talked about at the beginning. On the other side, though, we have the ventromedial pathways, and these operate autonomously. They originate down in the brainstem and control your proximal and axial muscles to manage things like posture and balance. So one system is all about deliberate action, while the other is constantly running in the background for foundational stability. Now, what's really interesting about this is the defining feature of the lateral pathways, the cortical spinal or pyramidal tract. This is the longest and, frankly, the most important motor tract in your entire body. It originates way up in the motor cortex, but as it travels down, it passes through the medullary pyramids. That's at the junction of the medulla and the spinal cord, and right there it crosses over. This crossing is called decussation. This anatomical crossover is the exact reason why the right side of your brain controls the left side of your body and vice versa. Pretty cool, right? There's also a secondary tract here called the rubrospinal tract originating in the midbrain, but honestly, in humans, its role has largely been completely taken over by the corticospinal tract. Meanwhile, those ventromedial posture highways are constantly working behind the scenes to keep you upright. We've got the vestibulospinal tracts using sensory data right from your inner ear to keep your head balanced. The tectospinal tract is rapidly constructing a real-time map to immediately orient your eyes towards sudden stimuli. And then the reticulospinal tracts act as your built-in anti-gravity system, liberating your muscles from reflex control and maintaining your standing posture against the relentless everyday pull of the earth. Moving right along to Section 4, the spinal cord execution. We finally arrived deep in the ventral horn, what we can call the factory floor of the body. All of that complex strategy we just talked about ultimately funnels down to lower motor neurons, known as alpha motor neurons. Now, a motor unit consists of just one single alpha motor neuron and all the individual muscle fibers that it innervates. And if you group a collection of these neurons innervating a single muscle, that's called a motor neuron pool. But the alpha motor neuron itself is so crucial because it's termed the final common pathway for behavior. Why? Because it is literally the only neuron that directly triggers the generation of physical force by your muscles. This is the exact moment where an abstract thought physically turns into action. But an alpha motor neuron doesn't just work in a vacuum. It receives its instructions from three very specific sources. First up, you have upper motor neurons from the motor cortex and brainstem delivering the voluntary command. Second, it gets sensory feedback directly from muscle spindles, telling it the current, real-time length of the muscle. And third, and this is absolutely vital, it receives input from spinal interneurons. Actually, spinal interneurons provide the largest source of input by far. They act as local coordinators on that factory floor, managing complex automatic tasks like reciprocal inhibition. Basically, this ensures that when your bicep gets the signal to contract, your tricep gets a simultaneous signal to relax. That's what allows for smooth, fluid movement rather than a jerky mess. Which brings us to Section 5, basal ganglia and cerebellum. So what happens when our movements aren't perfectly smooth? Well, your brain relies on some critical subcortical loops that basically act as outside consultants. The first one is the basal ganglia loop. Information cycles from the cortex down through the basal ganglia stridum and globus pallidus, through the thalamus, and then right back up to the supplementary motor area. Think of this loop as the ultimate gatekeeper. It helps select and initiate the willed movements you actually want to do while actively suppressing the inappropriate ones that you don't. It's the essential filter that keeps your physical actions intentional and controlled. The second consultant is the cerebellar loop. Now, the cerebellum is often called the little brain, but man, it punches way above its weight class. Think of it as your body's predictive physics engine. It is constantly comparing the intended movement goals coming from your cortex with the actual real-time physical position of your body. It calculates the precise timing and the exact force required for multi-joint movements, and it actively corrects errors on the fly. It is absolutely essential for motor learning. Whenever you learn to ride a bike or, play the piano, you really have your cerebellum to thank for hardwiring that precise physical timing. We have covered a tremendous amount of ground in this explainer today. We've mapped the exact anatomical wiring of physical action, from the highest association areas in the brain, down through the medullary pyramids, right to the alpha motor neurons sparking your muscle fibers. We know exactly how a voluntary movement is executed. But I want to leave you with a question to ponder on this final thought. We know the mechanics, sure, but where exactly does the pure will to move truly begin? In all this incredible, beautifully complex biological circuitry, where does consciousness step in and declare, I choose to snap my fingers? It's a profound mystery that bridges the gap between biology and philosophy, and it's one that scientists are still working to unravel today. Thank you so much for joining me, and keep exploring.